Hello all, welcome to part 3 of the STV series. So today we'll be discussing about the technologies which can be used to realize the software-defined vehicle. In order to have any software-defined vehicle capabilities in a vehicle, there are basically few constraints. I have just discussed about five, but there might be even more than five, which are basically the bottleneck for the STV. So the first one is the resource limitation. The second one is the ability to support different apps. Third one is a standardized interface irrespective of the hardware. Fourth one is ease of app deployment, and fifth one is to avoid system failure as much as possible. So we will be discussing about each one in a separate slide. So, unlike cloud, which almost has unlimited resources, we are talking about a vehicle which is a resource constrained system. So you don't have the flexibility of having unlimited resource. So you need to get your things done within a limited resource. So you might be having a module which is very much resource constrained compared to another module, like an infotainment system is way more powerful compared to a telematic system. So in that case, if you want to have SDV enabled systems for each of these, then basically you need to keep in mind with respect to the resource constraints. Second part is you're talking about having third-party apps running on your system. So a third-party app cannot the better idea would be that a third party app can be of any programming language, and if you have the capability of running that on your particular device, that is way better rather than restricting the person to have a specific app built on a specific language. If you do that, basically you are uh, closing the doors for better flexibility, and this will basically discourage the people in even pursuing or developing specific apps with respect to that. So basically, you need to have the capability of handling multiple apps of different programming languages. Third part is standardized interface, irrespective of hardware. So what does it mean is, think about this game, Temple Run. Okay. Now, this game basically needs some three or four inputs. So it could be your accelerometer, gyroscope, and it will be your touchscreen. Irrespective of the hardware, means you can have a low-end phone, you can have a medium-end phone, or you can have a high-end phone. In all these three, the app developer basically what he does is he has built an app where he is basically speaking to an interface or a signal which is having a unique name. So the advantage what we have in an Android or an iPhone ecosystem is, irrespective of what the hardware is, the name in which a particular sensor data is called, it stays the same. So in a low budget phone, it will be your accelerometer x-axis. Similarly, for a high budget phone also, the name of the variable will be the same thing, not be any different. You will have a better capability with respect to the sensor, but with respect to naming of the sensor, it stays the same. As the naming of the sensor stays the same, whatever hardware you are deploying your app, as the naming is same, basically you have the ease of deployment. You need not modify your app for a specific target hardware, because if you do that, basically it will be very tough for you to maintain and scale the system as a third party developer. And ease of deployment, what it means is, say there is a update which your phone gets. Okay. Now, in order for the like a firmware update. Okay. So, in order for the complete updation to happen, basically you have to. So basically, what it does is it restarts the entire phone, And the new updates basically reflect once the update have been completely done. This is with respect to the firmware update. Now, if you're talking about an app update, basically what happens is, say there is an app called maybe Facebook app. Okay. Now there are updates available for this Facebook app. So I update the Facebook app. Updation of Facebook app doesn't have any other side effect on the rest of the apps or the rest of the Android or iOS OS which is running there. So Facebook app updates on its own. So this kind of capability should also be there in a vehicle because say one specific app has an update available and it wants the particular app to be the vehicle wants the app to be updated, then basically it should not lead to a complete system reboot for just for the app to update. The app as such should have the capability of getting updated on its own, or maybe like it should have the capability of getting updated without affecting any other system. So that is what it means. And the fourth one is uh, a failure of app should not lead to the entire system failure. So because it will be catastrophic. So you have one app running in a vehicle which has gone wild. And if that is the case, basically the consequences or effects of that particular thing should be restricted only to the specific app, but it should not lead to the entire overall system failure because that is the core functionalities of the vehicle should stay the same. All the rest of the functionality should function as per its as per its rules and restrictions. And any rogue app should basically be very much confined to its own domain or its own space. Now, to realize SDV, there is no standard technology which is accepted across all the OEMs and suppliers and all the key players as a whole in the industry. So there are multiple ways in approaching this SDV, realizing this SDV, and I will be touching upon five of these techniques which are basically being used for realizing SDV. There might be even more than this. I am not aware, but I can only talk about what I know. So these are the list of technologies. One is Android Automotive. Second one is virtualization using hypervisor. Third one is AUTOSAR. Fourth one is the classic OTA, which is basically on the field, well tested. The fifth one is container-based OTA. So if you're talking about Android Auto, so Android Auto is basically an extension of the Android OS, which is basically used in mobiles. So the pros of this particular system is it is quite stable. It has a very strong ecosystem, and the support system for this is running for the past 15 years. So it is quite robust system. But the main problem with Android Auto is basically it has vendor lock-in, which is something which these OEMs are basically not comfortable with. And on top of it, I have seen Android Auto running on the infotainment systems, but I am not very sure whether it has applications beyond infotainment systems. This is something which I am not aware of. So yeah, if there are something, please do write in the comments so that it will be learning even for me. So these are some of the pros and cons of Android Auto. So coming to the next thing, so this is basically virtualization using hypervisor. So basically what hypervisor is, you have an hardware, you have a hypervisor on top of it, and using this hypervisor, you can spawn multiple VMs using this hypervisor. Okay. When you're talking about a VM, basically virtual machine is like a machine inside a machine. So this is how the virtual machines architecture look like. So you basically have a hardware over here, and you have a kernel. For example, you can take it as a Linux kernel, and you do have a hypervisor over here. Okay. Now on top of it, basically two virtual machines are spawned. Each of this virtual machine will be having its own OS altogether. So you can have a Maybe Debian OpenSUSE a Linux kernel over here, and you can even have a guest OS which is running on Ubuntu. Okay, and this basic virtual machine, both of these virtual machines are completely isolated with respect to each other, and it has a far better isolation compared to a container. Okay. Now, there is this SLD rated operating system which is used in automotive space, which is QNX, which basically gives you the capability of hypervisor, as it is already SLD certified software, certified OS. Basically, it is well tested in the automotive space, and it has the capability of spawning multiple VMs. But the problem basically with hypervisor is, you see the guest OS over here. This basic guest OS is something which is a full-fledged OS of its own. Like, say, if there is a Windows machine and you want to have a virtual machine of say Ubuntu, and say you have to run one C++ app. If your goal is to run a C++ app in one virtual machine, and your goal is to run a Python app in another virtual machine, say the C++ app is some 10 MB size, and maybe the Python app which may be needing some 20 or 30 MB by running the Python interpreter and all that. Basically, to do that, you have to spawn two different virtual machines. Both, for example, can be of Ubuntu. Each of this Ubuntu will consume at least 1 to 2 GB of space for the installation of the VM. And on top of it, you will be running a C++ app over here, and similarly, you will be running almost a 2 GB OS over here, and you will be running a 50 MB app, Python app over here, which basically makes no sense. So this is the main problem with VM, where if you want to deploy a app which is small in size, if you're it is like you're going to grocery shopping on a helicopter. You don't need a helicopter to go for a grocery shopping. You can go by walk, or you can take your cycle or a car to do it. You don't. It's basically an overkill if at all you are using a virtual machine to run small apps. It makes no sense. Okay. And the ease of deployment of third-party apps is also something which is not so smooth in this VM space. The fourth, third one is basically the AUTOSAR. I I don't have much of information, but I read somewhere that AUTOSAR basically use the adaptive AUTOSAR they uses the virtualization technique for SDV and for enabling SDV. This is something which I'm not that aware of. Maybe you guys can check it out. The fourth way of doing is the classic quota. So classic quota is what which is already out there. So this is what Tesla and other companies they have been actively using. So in classic quota, basically what happens is you already have the softwares in the car, and say there is an update available. So there will be a centralized system basically which will be triggering the cloud, and the cloud will be informing the vehicles that there is an update available, and as and when the vehicle is in a state of taking these updates in, the update mechanism will kick in. Basically, it will pull the just the app and the part of the app or delta change of the app, which will be pulled in, and it will be updated. The firmware will be updated. There are some issues with the classic quota, and the issues are as follows. Say you have an app which is of C++. Okay, your runtime which you are using is C++. Obviously, your app should also be of C++. Okay, first we will go with the pros. The pros is it is extremely light because you're only pulling the app, the binary, whatever is needed to run the app. And second thing is it's a proven technology. Now coming to the cons, basically you are having a C++ runtime over here. So all the apps which are basically running on this particular platform should be of C++ only. Okay, so that is like you are locked by specific programming language. which leads to a problem where the third party app development cannot happen in language other than C++. And the other problem is these C++ apps will not have complete isolation. And on top of it, if at all you want to run this particular this app too, you are doing an update for app one itself. Basically, you need to do an overall update of the. It means it will be so it is not possible that app one is running and app two is getting updated. If app 2 has to get updated, the overall system as such has to get an overall update. So there is an overall downtime for all the apps which are basically running in this space, irrespective of any of the app getting the update. So this is one major problem with the classic OTA. Now coming to the fifth way of doing, it is basically the container-based OTA. So here in this diagram, I'll just explain you with a small example with respect to how different is container and VMs are. Okay. So if you see both of them are having a hardware, both of them are running a Linux kernel or whatever kernel. For example, we'll consider Linux kernel. And now instead of a hypervisor, you have a Docker or anything similar to Docker. So it could be LXC, it could be Podman, it could be Containerd, or it could be anything else. Okay. Now, if this is an app which we are targeting to run uh, in the VM space, basically you have a guest OS and you run an app. But in a container, you run this app. For example, what we consider is the guest OS which is used over here is an Ubuntu 18. Okay. Now the Ubuntu 18 or Ubuntu 20 is basically 2 GB of size. After installation, it will be more than that. Okay. Now, say the app is some 50 MB is the size of the app which you want to run. Okay. So this makes no sense. Now, when you come to a containerized app, you want to create a container on an Ubuntu 18 image. So the basic Ubuntu 18 or Ubuntu 20 image which is available out there will be of size 100 to 150 MB. I think it is 117 MB. I'm not very sure. Okay. With that being the Ubuntu image, on top of it, you will have the bare essentials needed for running this app. Maybe you, and once those essentials are installed, you basically run this app. So you have 120 MB of base image, some 30 MB of essential softwares to run this image, which makes it 150, and you have an app of size 50 MB. So within 200 MB, you can run this app. Whereas over here, you will be spending almost 2 GB, so 2.05 GB. So 2.2 GB for the OS and 50 MB for the app which you are trying to run. Okay. So this is basically the primary differentiator with respect to the advantage of having a container-based OTA compared to a virtual machine-based OTA. Okay. Now on top of it, uh, the advantage what you get is, say if you compare to this image, basically you have a hardware, you have a Yocto specific Linux, and you have one app which is running on C++. Because of this particular arrangement, you are forced to have second app as C++ only. So this is the classic quota case. Okay. Now, if we come to the container-based OTA, you have the same hardware, you have the same OS running, you have the same app one which is running in C++. But if you have two apps, one is a Python app and one is Java app which you want to run, basically what you do is you run a Docker instance or you run any container instance over here. Once you run a container instance over here, on top of that, basically you can have as many apps as possible where each app could be of any language. So that is what we are trying to, that is the advantage when you go with a container-based OTA. So if at all you go to the first slide which we were discussing, so the ability to support different apps of multiple programming language. This is possible using container-based OTA. Standardized interface is something which is irrespective of whatever mechanism you're trying to deploy. Ease of app deployment is very simple in container-based OTA because you have a lot of infrastructure and lot of techniques available because container-based update is quite popular in the cloud world. So basically, the replication of what was done in cloud is being brought into the embedded world. So you do have a lot of proven techniques to handle those scenarios, and each of this container is basically a is completely isolated from any other container. So it is isolated, but it is not as isolated as a VM, but it is isolated good enough. So say one of this app fails, it doesn't lead to the entire system failure. It is only restricted to that particular app only. And as I have mentioned with respect to the space limitations and all, a container-based solution is basically better with respect to limited resource handling, but it falls in between the hypervisor and the classic quota, because in classic quota, if at all you come to the classic quota scenario, you don't have any. This is basically the best way of doing. What I mean is, you have two apps to run, each is 20 MB. So you have one app running 20 MB, you have second app running 20 MB, and both of them within 40 MB, you're done with your work. Okay. Now, when you come to a container-based app, you can't run the same two apps for 20 MB because you have a 120 MB of base image. You have some 30 MB of installations on top of this base image, and you have a 20 MB over here. Means 120 plus 30, which is 150, and you have 20 over here, which is 170. So 170 plus 170, it is 340 MB is needed to run the same 40 MB which we have discussed over here. So you need 40 MB of RAM space to run these two apps, but to do the same job using container, you have to spend 340. But if you go the VM way, it will be in GBs. Okay. Now this is where you, as a architect or whatever, you have to figure out what is that which you want. If you are speaking about a system where you want to give absolute flexibility to the developer, where the developer can have his app in whatever language he wants, then you have to go with the container based technique, where you have to live with its downside that you're replicating the same the OS. Means you are spending an extra 150 MB every time you want to deploy an app, but you get an advantage of having whatever programming language you want, and you will have absolute isolation. And if at all there is an update, each of this app can be updated irrespective without touching any other app or the entire system as such. If that is something which is your priority, you can go the container way. But if you are completely okay having only one specific programming language running, and if you're completely okay restarting the entire system as and when there is an update, if you're okay with it, then you can go with the classic quota way. Okay. Now, with this, basically, I have given an overview of the various techniques which can be used for realizing this SDV. In the next session, basically, we will have a deep dive into container-based OTA. I am basically working in this space, so I would like to give better insights and some of the real world challenges which you face when you are basically trying to implement this container-based OTA in a vehicle. Thank you.